Okay, welcome back to number theory. Today I'm going to talk about Euler's theorem and Fermat's little theorem. And these are two theorems which have to do with modular arithmetic. So if we recall, last time we talked about z mod nz, and this is the integers modulo n. And namely, last time we showed that, well, we showed that if a in z mod nz is, well, not if, I should say a in z mod nz is a unit if and only if the GCD of a and n is equal to 1. And this will be kind of the key thing that we use today. And let me just state the two theorems. So first we're going to do Fermat's little theorem. And Euler's theorem is a generalization. And this says if the GCD, or if P is prime, and P does not divide A, then A to the P minus 1 is equivalent to 1 modulo P. So this is Fermat's little theorem. And now, to state Euler's theorem, I have to define the so-called Euler-totient function is a function from the natural numbers to the natural numbers. So it takes in positive integers, it gives me out positive integers, and phi of n is going to equal the size of the set of elements between 1 and n, such that the GCD of a and n is equal to 1. So, for example, phi of 1 is equal to 1, phi of 2 is equal to 1, phi of 3, this is 1, phi of 4, well, what has GCD 1 with 4, so this will be 2, phi of 5 is 1, phi of 6, this gets interesting, so 1 has GCD 1, 2 does not, 3 does not, 4 does not, but 5 does. So, oh, I lied. So this is 2, because here we have 1 and 5. Here, for 2, we have 1 and 2. Here we have 1, 2, 3, and 4. Here we have 1 and 3. Here we just have 1. So these are the sets of things with GCD 1 that is less than n. And so from this you might pick out some patterns, and namely, probably the easiest pattern to pick out is if P is prime, the GCD, or not the GCD, the Euler phi function of P is P minus 1. So how can we prove this? we just note if we have an element less than p, then GCD of A and P is 1. Because the GCD of an element in prime is either 1 or the prime, but since it's less than the prime, it has to be 1. So this tells us that the set of elements between 1 and P, such that the GCD of A and P is 1, so this is actually just equal to the set 1 to all the way to P minus 1. Alright, so just stating the so this is what the Euler-Toshin function is. So now we can state the theorem due to Euler. And this says, if the GCD of A and N is equal to 1, then A raised to the phi of N is equivalent to 1 modulo N. So maybe we'll note Euler's theorem implies Fermat's little theorem. And this is because if P is prime and P does not divide A, so this tells me GCD of P and A is 1, then we have A to the phi of P. Well, this is just A to the P minus 1, because we showed up here that if P is prime, phi of P is P minus 1. This is 1 modulo N. Well, P here. So Euler's theorem implies Fermat's little theorem. Alright. So this is our goal, and let's do this. So to do this, first I'm going to define the group of units modulo n is, so we're going to note it z mod nz, and then we're going to put a star here. So this is just going to be the set of elements, or I guess you should think of these as equivalence classes, in z mod nz, such that, if you recall, it's a unit, which means it has an inverse, such that there exists some b in z mod nz with a times b equivalent to 1 modulo n. So this is kind of the set we're going to study. And first, I don't know how I want to do this. Let's just say the size of the group of units is equal to the Euler-Toshin function of n. And to prove this, recall, so recall from last time, we have that 0, 1 to n minus 1 is a system of representatives for z mod nz. And we also showed that A is a unit in z mod nz if and only if the GCD of A and N is equal to 1. And to give kind of a quick refresher of the proof, use the extended Euclidean algorithm. And this gives us that there's AB plus Cn is equal to 1. So B is the multiplicative inverse. of A modulo n. So thus we see in the other direction you say, well, if the GCD is not 1, then we can find the zero divisor, and we know units are not zero divisors. So that's kind of the other direction. So this tells us that the set of units z mod nz star is equal to the set of A and z mod nz, such that the GCD of A and n is equal to 1. And the size of this, so the size, just by definition of the Euler-Toshin function, the size of this set is the Euler-Toshin function. So we've just related the group of units modulo n to the Euler-Toshin function. So now let me define what a group is. So a group is a set G with a binary operation. So think of it like a multiplication. And usually we denote it by star or something, from G cross G to G. So all you're doing is you're multiplying two elements, such that the following axioms hold. 1, 2, and 3. We have, there exists an element 1 in G, such that 1 times G equals G times 1 equals G for every G in G. 2, for every G in G, there exists some H in G, such that G times H is H times G, which is 1. So this is the inverses. This is the unit or the identity. And the last one is we want associativity. So for every GHK in G, we have G times H times K is equal to G times H times K. So this is associativity. Note, in general, we don't have a commutativity property. So a group is abelian if for every GH in G, we have G times H is H times G. So you can also multiply them. So we kind of defined the group of units. And we said, abstractly, it's this. And of course, Z mod NZ, we showed last time that's a ring. So if we're calling this subset the group of units, we'd like for it to be a group. So I claim Z mod NZ star. So the group of units is an abelian group. So let's prove this. We note that we have 1 is in Z mod NZ star is the identity. Just by definition, we had the equivalence class of 1 in Z mod NZ, and it acts as, in that ring, it's the identity. So if we're considering just multiplication, then 1 is the identity under multiplication. So that gives us the identity. For inverses, no, by definition, if we have an element in Z mod NZ star, then that means there exists some B in Z mod NZ such that AB is equivalent to 1 modulo n, just by definition of what a unit is. And note, this implies that B is actually also a unit, since it has multiplicative inverse A. And then we note that associativity and commutativity follow from Z mod NZ being a commutative ring. That is, we had that the multiplication in Z mod NZ is already commutative and associative. Thus, when we look at this subset, this multiplication has to be commutative and associative. Oh, I guess there is one small thing we have to prove. That is, that if you multiply two units, then I want to show that A times B is also a unit. Because it's not necessarily clear that we're closed under multiplication. And to see this, we note that if A and B are units, then by definition there exists some C and D such that AC is 1 mod n, and BD is also 1 mod n. So if we consider AB and we multiply this by CD, so this is the same as AC times BD, which is just the same as 1 times 1, which is 1 mod n. So we are closed under multiplication. So that's kind of saying that multiplication is a binary operator on the group of units. So, great. We have that. So we just showed that the group of units is an abelian group. And now what I'm going to do is prove the following statement. Say we have some G is a group, and let's define a function or is a group, and let's define a function. I'm going to call it L sub G, and it's a function from G to G, where G is an element of G, and for H in G, we have that L sub G of H is just left multiplication of H by G. Then I'm going to say that this function L sub G is a bijection. So let's prove this. So we note to show a function is a bijection, it just suffices to show it has an inverse. So consider the function L of G inverse from G to G. We note for an element H in G, we have L of G inverse of H. Well, by definition, this is just G times G inverse of H, which is 1 times H, which is H. And similarly, L of G inverse of L of G of H is just going to be G inverse times G times H, which is just 1 times H, which is H. So L of G has an inverse, and hence is a bijection. All right, we are now ready to prove the two main theorems for today. So first, theorem by Fermat, Fermat's little theorem. If P is prime and P does not divide A, then A to the P minus 1 is 1 modulo P. So to prove this, what we'll do is, since P is not prime, or no, not since P, since P does not divide A, we have that A, when we think of it as an element of Z mod PZ, it's going to be a unit. Because since P does not divide A, the GCD of P and A has to be 1. Since GCD of P and A must be 1. Now, let us consider let's consider the following sets. Consider 1 times 2 times 3 all the way up to P minus 1. So what we're doing here is or maybe I should do it like as follows. I should write this in the following way. So consider the set 1, 2, all the way to P minus 1. And now, let us also consider the set A times 1, A times 2, A times P minus 1. So this is just the set of left multiplying by G, or by A, that we described above. So by the proposition above, we have that if this is X, this is L sub A of X. So this is a bijection, and namely, they're the same set, because this is a subset of the group of units, and namely, since it's a finite set, so they're actually equal. So now, let us multiply all the elements together. That is, let us multiply all the elements of X, and since these two sets are actually equal, let's just multiply everything in this set together. So on one hand, we get 1 times 2 times 3 all the way to P minus 1. So this must be equivalent to A times 1 times A times 2 all the way to A times P minus 1. This is, of course, modulo P. But now, let us just regroup the terms. So this, let us write as let us write it as P minus 1 factorial. If you just pull out all the A terms, you get a factor of A to the P minus 1, and you also get a P minus 1 factorial. and this is mod p. And let us note p minus 1 factorial is a unit since it is a product of units. Since it is a product of units, so we can cancel it out. Just multiply by the element by p minus 1 factorial, whatever you can multiply that by to get 1. And this tells us that 1 is equivalent to a to the p minus 1 modulo p. And we're done. So that's how you can prove Fermat's little theorem. So now we can do the generalized version, which is due to Euler. And you'll notice that the theorems looks exactly the same. So if GCD of a and n is equal to 1, then a to the phi of n is equivalent to 1 modulo n. And the way we can prove this is the exact same way, except now let x equal the set of units modulo n. So note a is an element of x, and consider L sub a of x by the same reasoning. L sub a of x is equal to x. And now, let's say x is equal to, I don't know what the elements of x look like, so let's call it maybe x sub 1, x sub 2, but we know that there are phi of n such elements. And this is equal to the set a times x sub 1, all the way to a times x sub phi of n. And let's multiply everything together. And this gives us that x1 times x2 all the way to x sub phi of n is equivalent to ax1 all the way to ax sub phi of n, and this is of course mod n. And this tells us that, pull out the factor of a, x1, x sub phi of n, is equivalent to a to the phi of n, because there are phi of n a's on this right-hand side, times x1 to x sub phi of n, mod n. And again, we note x1 times all the way to x sub phi of n is a unit, so it can be canceled out. So when you cancel it out, this gives us that 1 is equivalent to a to the phi of n, and this is, of course, modulo n, which is exactly what we wanted to show. So yeah, this is Euler's theorem and Fermat's little theorem.